Welcome back to Bite-Sized Breakthroughs, where we break down complex research into digestible bites. Today, we're diving into the fascinating world of weight-agnostic neural networks with Dr. Paige Turner, a leading expert in this field. Paige, thanks for joining us.
It's great to be here, Alex. I'm excited to talk about this research.
To start, can you give us some background on this concept of weight-agnostic neural networks? What's the big idea here?
Sure. Think about it like this. We've been training neural networks for decades, but what if we could design architectures that could already perform tasks without any learning? Imagine a network that could do things like navigate a maze or classify images without needing to learn its weights. That's the idea behind weight-agnostic networks. Essentially, it's about finding architectures that possess innate capabilities.
That's a really intriguing concept. It almost feels like the neural network is born with some sort of inherent talent. What's the historical context here? Has anyone else explored this before?
It's a great analogy, Alex. We can actually look to nature for inspiration. Think about precocial species like ducks or lizards. They're born with a suite of abilities that they don't need to learn, like swimming or escaping predators. That's kind of what we're aiming for with weight-agnostic networks. The paper does acknowledge that this idea isn't entirely new. There's a long history of research and architecture search, particularly with algorithms like NEAT, which optimizes both the weights and the structure of a network. However, this research goes a step further by de-emphasizing weight optimization and focusing entirely on finding architectures that are inherently capable.
So, we're not talking about finding the best weights, but finding the best network structure itself. That's a real shift in perspective. Professor Spectrum, you've been at the forefront of this field for years. What are your thoughts on this shift in focus?
I think it's a very insightful and potentially groundbreaking shift. For years, we've been obsessed with finding better training algorithms and larger data sets. But this research raises a vital question. Are we focusing enough on the architecture itself? Could we be missing out on developing networks with powerful inherent capabilities? This paper is pushing us to think differently about how we design neural networks.
That's a great point, Professor. Paige, can you tell us more about the specific contributions and innovations of this paper? What are the key takeaways?
Sure. The paper introduces the concept of weight-agnostic neural networks, WANNs, and a search method to find these networks. The method works by evaluating the performance of various network architectures across a range of random weight values, effectively eliminating the need for weight training. They've shown that these WANs can perform remarkably well on various tasks, including continuous control problems and even image classification.
So they've actually found networks that can solve real-world problems without any learning of the weights. That's pretty amazing. What kind of performance are we talking about? Can you give us some concrete examples?
Absolutely. They tested these WANs on 3 continuous control tasks: cart pole swing up, bipedal walker, and car racing. For example, in the car racing task, the WAN controller achieved a score comparable to a baseline controller that used both a pre-trained variational autoencoder (VAE) and a recurrent neural network (RNN), even though the WAN operated solely on the VAE's latent space. This highlights the fact that WANs can achieve impressive results even with a simplified architecture.
That's impressive. And what about the MNIST dataset? How did the WANs perform there?
They achieved significantly higher than chance accuracy on MNIST using random weights. It's important to note that while CNNs, which are specifically designed for image classification, have been honed over decades, the fact that WANs can achieve such high accuracy with random weights is quite remarkable. It suggests that there's a lot of potential for exploring architecture as a key driver of performance, even in complex tasks like image classification.
That's a very compelling argument, Paige. Professor Spectrum, can you shed some light on how this approach differs from existing methods for neural architecture search? What makes it unique?
Sure. The paper differentiates itself by focusing on finding architectures that encode solutions intrinsically, as opposed to relying on weight training for performance. Traditional methods like neural architecture search, NS, aim to find architectures that are highly trainable, meaning they perform well after weight optimization. But WANs are different. They are designed to perform well even with random weights, essentially finding solutions baked into the structure itself. This approach also stands apart from Bayesian neural networks, BNNs, which learn the distribution of weights. While BNNs also utilize random weights, WANs focus on finding minimal architectures that are robust to a wide range of weights. The paper cleverly applies weight sharing, reducing the dimensionality of the weight space and making it much more manageable to explore.
So the WAN search method is essentially about finding architectures that are inherently capable of performing tasks without requiring complex weight learning. It's a bit like designing a network that already knows how to do things. That's a very different approach than trying to train a network to learn how to do things.
Exactly, Alex. And to do this, the paper uses a modified NEAT algorithm, a neuroevolution algorithm, for its search. This algorithm is designed to evolve the topology of the network, adding nodes and connections, and changing activation functions. The activation functions play a key role, encoding various relationships between inputs and outputs. It's a fascinating interplay of structural evolution and functional encoding.
It sounds like a very complex process. Can you walk us through the steps involved in the search method?
Sure. The WAN search algorithm can be broken down into these steps. First, we start with a population of minimal neural network topologies with sparse connections. Then, we evaluate each network by performing multiple rollouts with different shared weight values assigned at each rollout. We then rank these networks based on their average performance across these rollouts, considering both the performance and the complexity of the network. Finally, we create a new population by probabilistically selecting the highest ranked networks and applying topological operators to them. This process is repeated until convergence, gradually evolving the architectures to achieve better performance and simplicity.
So the search method is essentially like a breeding program for networks, where the most capable and efficient architectures are selected and modified to create even better ones. It's an evolutionary approach to network design.
That's a good way to put it, Alex. And it's not just about finding any old network. The method is also designed to find networks that are as simple as possible, minimizing the number of connections. This is inspired by the concept of minimal description length, MDL, from algorithmic information theory. Essentially, we're looking for networks that are concise and efficient.
That's really interesting. So they're not just trying to find networks that work well, but networks that work well with the least amount of complexity. It's like finding the most elegant solution possible.
Exactly, Alex. And that's a key aspect of this research. It's not just about achieving high performance, but also about achieving it with minimal computational resources and complexity. It's about finding the most efficient way to encode solutions within the network architecture itself.
Now, Paige, let's talk about the experimental results. What were some of the key findings, and how did the WANs compare to existing methods?
The results were quite impressive. Across all the tasks, the WANs achieved comparable performance to networks with trained weights. This demonstrates the power of finding architectures that are inherently capable. For example, in the bipedal walker task, the WAN controller achieved a similar score to a baseline controller that used 2804 connections, but the WAN only used 210 connections, a significant reduction in complexity. In the car racing task, the WAN achieved comparable performance to a baseline controller that utilized a pre-trained VAE and RNN, but the WAN only operated on the VAE's latent space. This highlights the fact that WANs can be very efficient and achieve similar performance with fewer resources.
So the WANs are not only performing well, but they're doing so with fewer connections, leading to simpler, more efficient architectures. That's a big deal, especially in terms of computational resources and energy efficiency.
Absolutely, Alex. And it's not just about computational efficiency. The fact that these networks can achieve high performance with random weights suggests that we may be able to develop models that learn faster and generalize better. This could be particularly relevant for areas like few-shot learning and continual learning, where agents need to adapt quickly to new information or tasks.
Professor Spectrum, what are your thoughts on these experimental results? Do they live up to the hype?
I think they're very exciting, Alex. They show that we can find architectures that possess strong inductive biases for specific tasks. This is a critical step in developing models that are not only efficient, but also robust and adaptable. While this research is still in its early stages, it has the potential to significantly impact the field of deep learning.
Paige, can you talk a bit about the limitations of this research and what future directions you see for this work?
Sure. The current approach is limited in terms of the complexity of the architectures it can discover. While it successfully finds minimal networks for the tasks investigated, it may struggle with more complex tasks requiring larger and deeper architectures. The search process is also computationally expensive, especially for more complex tasks. Further research is needed to develop more efficient search strategies. Finally, the current approach primarily focuses on continuous control tasks and image classification. Exploring the effectiveness of WANs on other tasks, such as natural language processing or time series analysis, could provide further insights into their generalizability.
Professor Spectrum, any thoughts on how these limitations could be addressed in future work?
I think there are several promising directions. One is to explore the use of WANs in combination with other techniques, like reinforcement learning with intrinsic motivation. This could lead to agents that can learn and adapt in open-ended environments. Another direction is to develop more efficient search methods, potentially incorporating recent advancements in differentiable architecture search. Finally, we need to explore the effectiveness of WANs for tasks beyond continuous control and image classification, like natural language processing and time series analysis. This would help us understand their potential across different domains.
That's great insight, Professor. Paige, what are the broader implications of this research? Where do you see this research heading in the long term?
I think this research has the potential to fundamentally change how we design and train deep learning models. If we can successfully find architectures that encode solutions intrinsically, it could lead to more efficient learning, improved generalization, and the discovery of novel building blocks for deep learning. This could expand the field beyond existing components and lead to truly innovative deep learning systems.
That's a very exciting vision, Paige. Professor Spectrum, any final thoughts on the potential impact of this research?
I believe this research could fundamentally alter our understanding of neural networks and how they learn. It's a clear indication that we need to explore the architecture of neural networks with greater depth and focus. This research could lead to the development of more efficient, adaptable, and robust deep learning models, potentially revolutionizing various fields like robotics, healthcare, and artificial intelligence.
That's a powerful message, Professor. Paige, thank you so much for joining us today and sharing your insights into this fascinating research. It's been a real pleasure.
It was my pleasure, Alex. Thanks for having me.
And to our listeners, thanks for tuning in to Bite-Sized Breakthroughs. We'll be back next time with another dive into the exciting world of cutting-edge research. Until then, keep exploring.